When I was reading this paper, I couldn't stop thinking about the idea of AI researchers having to find a bunch of like 14-year-old teenagers to be experts and teach to teach Voyager how to play Minecraft, especially in the human feedback section. Finding people who would be able to construct high quality plans for an agent in Minecraft is a niche recruiting requirement.
That'd be really funny. I could also see that. Man, there's probably some kids that had like their MIT maker portfolio. They're like, I was one of the Minecraft folks on the Voyager paper.
Oh yeah, it's like yeah, my parents were our Stanford professors and they needed someone to play Minecraft and I was there.
Wait, how did they use teenagers to train the model?
I'm sorry, what?
Did they? What were you saying about them using teenagers or something that played Minecraft to improve the model or something like that?
Oh, later on they talk about how for one component of the architecture, uh, they compare LLM feedback versus human feedback, and they talk about how in order to provide feedback as a human, you have to be a pretty high skill Minecraft player yourself. So I was thinking about the fact that if you're a researcher in Minecraft and you don't know how to play, but you need a human to train your agent, you would probably do pretty well to like recruit in middle school and find a bunch of little kids to teach your agent Minecraft because they're probably the most knowledgeable resource you could find. But
It's
I
just
guess we can
something
start the
that
recording now and get started. I'm sorry, did someone say something?
I was just going to ask, is that something like we're actually considering to do? Because, I mean, I've got a kid and his friends will happily do that, man, for us.
I guess like we're not using the Minecraft environment, so we won't need to, but and they didn't in this paper, but just the idea of trying to find Minecraft experts is what I was just making conversation on in the beginning before we start reading. So I think we can start the recording now. So we're talking about Voyager today, which is the first LLM powered agent that has a physical embodiment inside of space, and also has the ability to learn over its entire lifetime and learn new skills and then create new skills, as well as learn how to combine different atomic actions into sequences to achieve higher level goals. So Voyager consists of three components. The first is an automatic curriculum that gives the agent things to do and tasks to explore, which leads to increasing the agent's exploration and allows it to move further within this world, as we'll see later on in the results. The second component is a skill library, and for this specific paper in Mind Dojo, which is the like Minecraft harness they built for an AI. Here they chose to have the agent execute tasks and create tasks in code. So writing executable code, storing it, and then retrieving it and running it. There's also a new iterative prompting mechanism that incorporates environment feedback, execution errors from the code and the skills, as well as self-verification for program improvement, which becomes really important when the agent, Voyager specifically, is creating new skills. The ability for Voyager to self-verify and know whether the skill just created is working or not is a critical component of Voyager's ability to progress throughout the environment. So the skills Voyager develops are temporally extended, which just means they increase as time goes on. Interpretable and compositional, which compounds together to create an agent who has the ability to rapidly, or those things compound together to greatly increase the agent's abilities and alleviates the long-standing problem within LLM agents of catastrophic forgetting, where once the history goes outside the context window, if you're not doing a complex memory or skill library, like in this paper, an agent can learn a skill, and then once the history of it learning that skill goes outside its context window, it's like it never learned it. So all these different components of Voyager come together to enable lifelong learning, which is our arguably the high-level goal of Voyager is to create an agent that can learn skills progressively over a long time horizon. So this paper has great figures. Really, I think some of the best graphics of any AI paper we've read so far. So in figure 1, so the x-axis denotes the number of prompting iterations. So you can think of them as like run cycles or loops that's gone through, although it's a bit more complex. And then on the right, the axis is number of distinct items. So the orange and blue are Voyager with and without some oblations. Just the interesting thing to note here is that AutoGPT, before Voyager, was the state of the art for Minecraft in this harness they built. Although they actually ended up completely re-implementing AutoGPT in their own code, which they'll talk about later, but it's an interesting thing they had to do, apparently, to be able to get AutoGPT to be able to work within the domain of Minecraft. So building generally capable embodied agents that continuously explore, plan, and develop new skills in an open world is a huge challenge for the AI community, and arguably a description of what you would need to create a true AGI. So recent advances in LLMs, specifically in LLM-based agents, harness the world knowledge that's encapsulated in pre-trained LLMs, the common sense and just understanding of the world and the environment they have through an extremely large knowledge base. So that the LLM's ability and its pre-existing world knowledge allows it to generate action plans and execute policies and break down tasks into subtasks and execute them to accomplish goals. So while LLM agents are able to do a lot of things, they're not lifelong learners that can progressively acquire, update, and accumulate and transfer knowledge over an extended time period. So for this paper, they choose the domain, which is like the toy problem they give to the AI. They choose Minecraft, which is actually a quite complex domain, specifically in the way they implement it for Voyager. So unlike most games that are studied in AI, so some classical games in AI, the most famous is chess, of course, with Deep Blue by IBM in the 90s. There's been AlphaGo more recently, but also things like StarCraft and Dota 2 for especially in like the mid 2010s were like the state of the art for teaching neural nets how to play games, and those really complex, extremely high skilled human games. StarCraft specifically was a really big training domain for a lot of LLMs, or not LLMs, sorry, neural nets in the last decade. So Minecraft doesn't impose a predefined end goal or a fixed storyline as it's an open world environment. Instead, provides a unique playground with essentially endless possibilities. So Minecraft requires players to explore vast procedurally generated 3D terrains and then unlock a skill of trees or a skill of resource or a tree of resources they refer to as a tech tree for this specific implementation. But if you've ever played Minecraft, you gather resources, combine them, and then iterate to get better resources and tools eventually. So they argue that for creating a lifelong learning agent, they should have similar skills to human players when comparing them in the domain of Minecraft. So skills human players need to play Minecraft include proposing suitable tasks based on the current skill level and world state. For example, learning how to harvest standing cactus before iron. If the agent finds itself in a Minecraft desert biome instead of a forest biome. The second skill needed to play Minecraft is to refine skills based on the environmental feedback and to commit mastered skills to memory. So once you learn a skill, being able to remember it, and then in the future being able to consistently reuse the skill and re-execute it correctly. So, and then the third skill is the need to be able to explore the world and seek out new tasks in a self-driven manner. We'll see later on that a lot of the agents that are less able than Voyager often get stuck in a small local area within the map and don't explore nearly as much as the Voyager agent. So Voyager is made possible through 3 key modules, which, as you'll see, the 3 key modules they implement essentially cover the 3 key tasks that players need to master in order to play Minecraft. So the first Voyager component is an automatic curriculum that gives the agent tasks to do and in order to try get to build skills, learn, and explore. a skill library for storing and retrieving complex behaviors, and then a new iterative prompting mechanism that generates executable code for embodied control, so being able to do things in the environment, perform actions. So they use code because LLMs understand it as text-based, and you can do almost anything with it. And it's a good way to represent complex tasks that require like temporal ordering. So doing things one after the other, as well as like iteration loops, stuff like that. So Voyager interacts with an LLM through like a black box query interface, which is GPT-4, as well as or Voyager interacts with GPT-4, but then GPT 3.5 is used in some other things that we'll see in a little bit. So they use a combination of prompting and in-context learning in order to augment or prompt engineer Voyager by adding context information to GPT-4's prompts. So there's no model fine-tuning in this paper. GPT-4 is just used the base model. So more specifically, Voyager attempts to progressively solve harder tasks proposed by the automatic curriculum, which the automatic curriculum takes into account the exploration progress in the agent state in order to choose a task that is just right. It's like a Goldilocks of not too easy or not too hard. Because if your task is too easy or too hard, your agent often fails and isn't able to progress. So the curriculum is generated by GPT-4 based on the overarching goal for Voyager as a whole of discovering as many diverse things as possible. So this approach for curriculum generation can be perceived as an in-context form of novelty search, which is a prior algorithm and work within computer science. So Voyager incrementally builds up a skill library by storing action programs that it writes and tests. And those skills within its library are able to be chained together and combined to allow Voyager to complete more complex tasks successfully. So each program or skill within the library is indexed by the embedding of its description, which can be retrieved in a similar situation in the future. So this is probably the most interesting aspect, I think, personally, about why this specific tool library implementation is so powerful. The natural language description of each tool and what it does, and then embedding that within a vector database and then being able to query in the future really solves the problem of how do you teach the LLM what tools it should use for when, which is a really key problem with autonomous agents. And I think the natural language embedding and then using semantic similarity to find similar or related skills to the current task is a really great way to implement this. So complex skills can be, I'm sorry?
I just wanted to ask a question on that. Do we know if they're just doing like a similarity vector lookup, or if they're doing anything more complicated? Because I know we've like run into issues with trying to do effective lookup in memory, and I'm curious if we know here what the if it's like a naive vector query, or if there's anything more advanced going on under the hood. I'm guessing the naive vector query would work. I'm just curious.
I don't think they explain their distance metric or their specific similarity metric within the database. They just say they embed it and then query for related.
Okay, cool.
Yeah, that would be an interesting thing to see how they're determining similarity. I was also thinking it might be interesting to see what the embeddings for the code is, particularly with related functions that feed into each other, whether showing the LLM an embedding or querying the vector database based on embedding of the code itself would illuminate relationships that are interesting and can be useful for chaining together multiple skills to achieve tasks or accomplish tasks. So complex skills can be synthesized by composing simpler programs. So taking atomic actions and then composing them together and chaining them together to create complex skills, which can be used to accomplish complex tasks. So the ability to compose smaller actions into more complex skills allows Voyager's capabilities to compound rapidly over time and alleviates the catastrophic forgetting that plagues other continual learning methods and LM agents. So to address the problem of GPT-4 specifically being unable to reliably produce the correct code action in a single shot. Their solution for that is an interactive prompting mechanism. And the way this works is that it executes the generated program to obtain observations from the Minecraft simulation, such as the inventory listing and nearby creatures. So it just gets essentially the current state of the environment, as well as the error trace from the code interpreter. So the iterative prompting mechanism takes the first try at code that the agent just wrote, tries running it or interpreting it, and then feeds back the error trace along with environmental information to the agent. So then all that information is synthesized as feedback. GPT-4 synthesizes all its feedback and then uses it to iterate another time and refine its code. So it repeats this process until a self-verification module confirms that the task is complete, which would require essentially the task doing what it was designed to and running without any errors. So once the self-verification confirms task completion, they then commit to the program to the skill library, and then they query the automatic curriculum generation for the next milestone or next task to work on. Now that they've successfully verified or made and verified the current task or skill. So empirically, Voyager demonstrates strong in-context, lifelong learning abilities. It can construct an ever-growing skill library of action programs that are reusable, interpretable, and generalizable. So they evaluate Voyager against some other LLM-based agents, specifically React, Reflexion, and their own custom implementation of the AutoGPT architecture. All the agents are evaluated in MindDojo, which is an open source Minecraft AI framework. It's pretty high level, and the agents aren't getting individual pixel values or really running the Minecraft player themselves as much. It's more a framework to allow LLMs and advanced agents to learn skills, plan, and make high-level decisions. So Voyager outperforms the previous state-of-the-art, which is AutoGPT. It obtains more unique items, gets further down the tech tree, and does it faster, and also traverses longer distances within the Minecraft environment. So Voyager is also able to utilize the Learn Skill Library in a new Minecraft world to solve novel tasks from scratch. So if they have a Voyager implementation, they have built a bunch of skills and they wipe its memory but leave the skills, it's then able to relearn how to use its already pre-existing skills that it created in the past, even though it doesn't have a memory of that anymore. So
another follow-up.
Yeah, for sure.
So they mentioned that you mentioned there that they have kind of this high level input from Minecraft Dojo here, or MindDojo rather.
Yeah.
Do you know, is there somewhere here where it actually lists approximately what that looks like? Just because it's another piece that I haven't actually really looked into yet is what the actual input of this model looks like.
I think in the appendix.
Okay.
Yeah, like we're gonna go through a lot of the appendix because it is quite interesting. This paper. It's also MindDojo is open source, so you could probably look up the GitHub if you want to get an understanding of the architecture. So, like we talked about already, Voyager consists of automatic curriculum generation, a skill library, and then an iterative prompting mechanism. So the automatic curriculum component, so embodied agents encounter a variety of objectives with different complexity levels in an open world environment. So an automatic curriculum offers numerous benefits for open world exploration, ensuring a challenging but still manageable learning process, fostering curiosity-driven intrinsic motivation for agents. I guess the idea that agents have motivation or could be motivated intrinsically or externally seems like personification of an inanimate agent, but continuing. It also allows and encourages the development of general and flexible problem-solving strategies from the agent, as well as generalizable tool implementations. So the automatic curriculum in Voyager capitalizes on the huge knowledge base of an LLM within GPT-4 by prompting it to provide a steady stream of new tasks and challenges for the Voyager agent to complete. So the curriculum unfolds in a bottom-up fashion, allowing for adaptability and responsiveness to the exploration process and the agent's current state. So the curriculum generation is able to take into account the context, environment, and current state, as well as the current skill level of the Voyager agent to choose appropriate curriculum for the agent skill level. So figure 4 here goes over the skill library and the process of a new skill being generated. So a task is generated by the curriculum, with the automatic curriculum generation, then it's given to Voyager. And then Voyager then writes a program with its GPT-4 brain, then a program description, and then there's a validation step to make sure it's right. And once it is, once it's validated to confirm it's a valid skill, then GPT 3.5 writes a English natural language description of the program, and that natural English language description is fed into an embedding model, and embedding is produced, and that vector embedding is associated with the code of the skill. And the key and value of the vector and the code are put in the skill library to be able to be queried later on by Voyager.
So this so at the bottom of that figure, that part where it says task, craft iron pickaxe, how to craft an iron pickaxe, and it says environment feedback. So what is that really? Is that environment feedback output from GPT 3.5?
So, for example, like if the automatic curriculum asks the agent how to craft an iron pickaxe in Minecraft, then the environmental feedback is context like, do you have wood? Do you have iron? What's your current inventory? What are your skills? What's your current pickaxe level? So everything about the current state of the Minecraft environment. So those limitations will constrain and inform the agent's choices later on.
Oh, so this query embedding, is that does that consist of both the reasoning output, like both the output of GPT 3.5 as well as environment feedback, which comes from the Minecraft environment itself? Is it like two? Is it two parts to this? Or is it
Yeah.
like one
So
thing?
so the top part, figure 4, is about adding a new skill to the skill library. On the bottom part that we're talking about right now is about how a query is generated in order to try and find relevant and related skills from the skill library. So
Yeah, I'm just
yep. So the combination of the task as well as the environmental feedback, those are both combined, and then an embedding is generated from that big combined prompt, and then that is used to query the skill library.
okay.
Okay. Any other questions?
Yeah, one more thing. It says here top 5 relevant skills. So they pick 5 ones, and then do they like? I would expect them to pick one skill, right? Or do they test all 5 of them separately then? Or why is there 5?
So what they're doing is they're finding the top 5 most relevant skills to complete the immediate task, and they provide the descriptions of these 5 skills as context to GPT-4 when they're asking it to solve this specific problem. So they provide these 5 skills as essentially options for GPT-4 at every single prompting time.
So it basically uses them as building blocks for creating a new skill.
Exactly.
Skill, right?
Yep.
Cool.
Yeah. So when faced with a new task that's proposed by the automatic curriculum, in order to find the skills that are relevant, they leverage GPT 3.5 to create a suggestion for solving the task, which is combined with environmental feedback, and that's the query context. So then they take the top 5 most popular skill or relevant skills out of the skill library. So that's how both adding and querying from the skill library works, just a vector database essentially. So the curriculum unfolds in a bottom-up fashion, allowing for adaptability and responsiveness. Adaptability, and the curriculum is able to respond to the exploration progress and the agent's current state and skill level. So using this automatic curriculum generation, Voyager is able to progress to harder self-driven goals. It naturally learns a variety of skills, such as mining a diamond, which is a more advanced skill within Minecraft. like the progression of material types in Minecraft, very roughly. It's like wood, stone, iron, diamond. I might be mixing up a few, but there's a progression, which is just the point they're trying to make with that. So the input prompt for GPT-4 has a few different components. The first one is a directives encouraging diverse behaviors and imposing constraints. So these are pretty generic components of the prompt that are always there, and they give high-level goals. Like the ultimate goal is to discover as many diverse things as possible. The next task should not be too hard, since I, the agent, may not have necessary resources or have learned enough skills to complete it yet. This little almost like self-critique reminds me a lot of AutoGPT self-critiques, in the way that this critique is very generic and not very helpful. Essentially saying the next task should not be too hard is really not super useful for an agent or GPT-4 when it's trying to choose one. It reminds me a lot of AutoGPT when it just essentially says, I could have done better, without giving any context or explanation. So the next component of GPT-4's prompt is the agent's current state. So the state in the Minecraft domain includes the player's inventory, their equipment, nearby blocks and entities, the current biome they're in. There are like several different biomes in Minecraft. The current time in the game, the player's health, their hunger bars, and their position within the world. So the prompt also includes previously completed and failed tasks. So this allows the agent to reflect on what it was able to and not able to accomplish, which should hopefully allow it to understand its abilities and not get stuck in loops of repeatedly trying failed tasks. There's also some additional context. When writing the prompt for GPT-4, they use GPT 3.5 to ask self-questions based on the agent's current state and exploration progress, as well as to self-answer those questions with a wiki knowledge base of Minecraft knowledge. And those combinations of questions and answers created by GPT 3.5 are provided as additional context to GPT-4 in its prompt. They mentioned they use GPT 3.5 to produce these little question-answer context pieces instead of GPT-4 just because of budgetary cost. Like, it's an interesting example of how you can use GPT 3.5 oftentimes as a helping agent for creating better prompts and assisting GPT-4. I think it's an interesting development in the field.
Well, why don't they just use GPT-4 for this as well instead of 3.5?
Oh, cost. Yeah.
But I mean, do they run this part, the 3.5 prompts, more than the four prompts or something?
They, like, on a total token level, it seems like they probably generate a lot more tokens on every iteration loop with GPT 3.5, because a lot of the prompt is for GPT-4 is generated by GPT 3.5.
Yeah.
And with this library, the AI could potentially improve tasks and the learning skill libraries over time, combinations, potentially corrections, keeping it up to date.
Yes. Yep, we'll get into that in a little bit. But yeah, it's able to iterate on its skills within the library. Okay, so with the skill library, the first component of Voyager is the automatic curriculum generation. With the automatic curriculum consistently proposing increasingly complex tasks, the next essential component of the architecture is a skill library that serves as the basis for Voyager's ability to learn and evolve. So the authors were inspired by the generality, interpretability, and universality of computer programs, and therefore that's why they represent each skill as executable code. And they also write some scaffolding that temporally extends actions for completing a specific task proposed by the automatic curriculum. So they write a little bit of structure to allow GPT-4 or Voyager to interact with the Minecraft environment through code. So the input to prompt GPT-4 consists of the following components. So the first one is guidelines for code generation. These are generic guidelines that are in every prompt. Things like telling the agent that their function will be reused for building more complex functions. Therefore, you should make it generic and reusable. I think that's a pretty good idea for a prompt, and would probably help out a lot of people who are writing code in AutoGPT. So the second component of the prompt is control primitive APIs and relevant skills retrieved from the skill library, which are crucial for in-context learning to work well. Does anyone here understand what they mean by control primitive APIs? Does that mean like how to control the agent within the Minecraft environment?
Sorry, I'm getting caught up on something.
Yeah, if I look at figure 4, if you look at that code snippet, there's things like where they use the bot and they say bot equip sword. Like, isn't those maybe what they refer to?
Okay, yeah, that might be the control primitive API.
Oh, it's on page 25. There's a list of control primitive APIs provided by Mindflare. So it's like Pathfinder go to place and like go get block. It's some rudimentary APIs that were provided by the underlying agent for Minecraft.
Oh, nice, perfect. Thank you so much. That was really helpful.
Granular control, I believe the agent has.
Next component of the prompt for the skill library component of Voyager is a component of the prompt that includes the generated code from the last run or within the run loop, the environmental feedback, execution errors, and then self-critique, which is given by GPT-4 to itself. So the final component is the agent's current state, which includes essentially a description of the Minecraft environment. They also include a component of the prompt to elicit chain of thought prompting, which essentially be something like reason step by step, write out your intermediate steps before doing anything, and then only after writing out a multi-step plan, generate code. So they're able to, Voyager is able to iteratively refine the program that it writes for accomplishing a skill through an iterative prompting mechanism, which is incorporated into the skill library as a new skill, and then the skill library index of the embeddings of its description. So for skill retrieval, they query the skill library with the embedding of the self-generated task plans and environmental feedback. By continuously expanding and refining on its skill library, Voyager can learn to adapt and excel in a wide spectrum of tasks, consistently pushing boundaries of its capabilities in an open world environment. Iterative prompting mechanism, which is the third component of the Voyager architecture. So the components of the iterative prompting mechanism are including environmental feedback, which illustrates the intermediate progress of the program execution in between different runs. They include some primitive control APIs to allow the bot to get environmental feedback and prompt itself within programs. They also include execution errors, as well as feedback from the self-verification module. The self-verification module checks for whether the task has been successfully implemented and whether the code successfully is interpreted. So essentially, GPT-4 is the self-verification agent. By providing Voyager's current state and the tasks GPT-4, they have it act as a critic and inform Voyager whether the program it just wrote achieves the task it was set out to accomplish. So their specific self-verification component builds on a lot of prior work within the space on self-critique and self-reflection, but it's more comprehensive than the current state of the art for that subfield of AI agents. So during each round of code generation, they execute the generated program to obtain environmental feedback and execution errors. This iterative process is repeated until the self-verification module accepts the task and adds it to the skill library. If the agent gets stuck after 4 rounds of code generation, still isn't able to complete the task, then they just move on to another one and ask the curriculum generator for another task. So this iterative prompting approach improves the program synthesis for embodied control which enables Voyager to continuously acquire new and diverse skills without human intervention or guidance. So they use GPT-4 and GPT 3.5 Turbo. They also use Ada, the OpenAI model, for embedding. The temperature is 0 for everything except for the prompts in the automatic curriculum generation component, which use a temperature of 0.1 to encourage task diversity, which probably helps with inducing exploration in the agent. So the baselines they compared against, there weren't really any LLM-based agents that were able to, on their own, work within MindDojo or Minecraft before this paper was written and the authors implemented it. So they ended up implementing React Flexion as well as AutoGPT essentially on their own within the framework and harness of MindDojo. So AutoGPT was by far the most capable, really the only prior work to this that was able to do anything in Minecraft. But compared to Voyager, AutoGPT lacks the skill library for accumulating knowledge, as well as the self-verification module for assessing task success. And also doesn't have an open curriculum or an automatic curriculum generation component for eliciting open world exploration from the agent. And also here, they just note that there's a lot of prior work within AI about giving essentially the exact screen pixel values and low-level outputs and inputs to agents, but that's not the goal of this paper, and they didn't want to essentially do like a reinforcement learning paper on Minecraft, which is what you would end up doing if that's how you set up the agent structure. Yeah, their focus is on GPT-4 and giving it the ability to learn over a long lifetime rather than solving a 3D perception control problem. So Voyager explores a lot more, discovers more items, discovers more novel items in a faster time frame. Comparatively, AutoGPT lags considerably in finding new items, while the other prior works like React and Flexion were essentially unable to do almost anything. I guess I was surprised AutoGPT was able to do as much as it did within Minecraft. I guess it surprised me. So the Minecraft tech tree tests the agent's ability to craft and use a hierarchy of tools. As the agent progresses through this tree, moving from, for example, wooden tools to stone tools to iron tools to diamond tools, progressing through the tree in that way requires the agent to master systemic and compositional skills. Compared to prior works, Voyager unlocks wood at a faster level, and Voyager is the only one to unlock diamond within the tech tree. So the outcome of that is it underscores the importance of all the new contributions that Voyager made to the field in this paper. Voyager traverses the map more, just goes further. These are just some results from the agent's ability to complete skills, how many attempts it took, and how many iterative cycles it took. So the fraction is its success rate out of trying 3 times, how many times did it succeed, and then the number is the number of essentially execution loops that were needed for the agent to complete the specific task. So they want to evaluate zero-shot generalization, which is when you give an agent a new task with no context or examples. In order to do that, they clear the agent's inventory, reset it to a new instantiated world, and then test it on unseen tasks. For both Voyager and AutoGPT, they both use GPT-4 to break down tasks into sub-goals and subtasks. It's interesting to note that they also compared AutoGPT base versus AutoGPT with the Voyager skill library. And the Voyager skill library was able to integrate with AutoGPT and was able to take advantage of it. And it significantly outperformed the baseline AutoGPT implementation. So that shows that the Voyager skill library they implemented here could likely be transferred and implemented in a lot of other agents in a pretty easy way. They also do some ablation studies, which is where they remove a component from the architecture, and then based on the delta between the full architecture and the architecture with the component removed, they're able to see what that individual component contributed to the overall architecture's success. So they found the automatic curriculum is crucial for the agent's consistent progress. The discovered item count overall within the world drops by 92% if the curriculum was replaced with a random, essentially task generation within the Minecraft universe. And that's because certain tasks may be too challenging early on within the agent's lifetime, particularly if they're attempted out of order. And if you're choosing a random task, the task generator doesn't understand the composition of tasks required. So on the other hand, manually designing Minecraft requires a lot of Minecraft-specific expertise. Maybe this is where they could do some RLHF from teenage Minecraft users. So Voyager without a skill library exhibits a tendency to plateau in the later stages, which I guess I know I've personally seen in AutoGPT. So this underscores the pivotal role that the skill library plays and its importance both within Voyager as well as AutoGPT. The skill library allows Voyager to create more complex actions and steadily pushes the agent's boundaries by encouraging the new skills to be built upon older ones. So I think the combination of the skill library, where the agent's able to consistently and reproducibly use skills, and the combination of that with an automatic curriculum generator really allows Voyager to inch up a bit by bit and make significant progress over a long time horizon within the game. So self-verification is the most important of all the feedback types, which makes sense because knowing whether or not, if the agent's working on a current task, like implementing a single skill within code, knowing whether or not that skill was correctly implemented is a very difficult problem. And if the agent either gets incorrect or no information about whether it successfully completed this task, oftentimes it won't have, because most self-verification runs require a few iterative loops of writing code, running it, it fails, sending the error to GPT-4, and then iterating. So the ability of the self-verification model to know when it's time to move on is very important. And then GPT-4 is a lot better at coding than GPT 3.5, which isn't exactly surprising. So Voyager has the potential in the future to be augmented with multimodal perception, while GPT-4 at the time of writing this paper, and still now, is text only, although OpenAI has the multimodal GPT-4 locked away somewhere. The authors of the paper are able to demonstrate that given human feedback, Voyager is able to construct complex 3D structures in Minecraft, such as a nether portal, which is it's a part of the game. It's a bit too complex to explain exactly what role it plays, but so the two kinds of feedback are the human as the critic, which is equivalent. So the human in this role is playing the role of the self-verification module within Voyager. So humans provide a visual critique to Voyager, allowing it to modify code from the previous round. This kind of human Voyager feedback. Oh, thank you, MJR. Yeah, exactly. Yeah, the Nether portal is the endgame achievement. There's a long process to get there, but it's essentially like a crucial skill if you want to quote unquote win Minecraft. So the human feedback is also really important for Voyager's ability to construct complex 3D structures within Minecraft, as Voyager is not able to perceive spatial or visual details. The human can also provide curriculum, where it takes the role of Voyager's automatic curriculum component. So humans will break down a complex high-level task into smaller steps with atomic actions, which then guides Voyager to complete them incrementally. So the human takes the place of breaking down the extremely high-level task into subtasks and then moving through them. So this improves Voyager's ability to handle more sophisticated 3D construction tasks, because the process of envisioning a complex 3D structure and then thinking about all of the individual tasks you would need to take to complete it is essentially requires spatial reasoning and spatial understanding, which is something that Voyager is not really capable of at the time. GPT-4 is really expensive. It's 15 times more expensive than GPT 3.5. Although they say specifically for code generation, it's unquestionably worth it because GPT-4's code generation ability is really almost in a different world compared to 3.5. So despite the iterative prompting mechanism, there's still cases where the agent gets stuck or fails to generate the correct skill. So the automatic curriculum has the ability to reattempt this task at a later time when the agent might be have learned more, have more skills that will allow it to complete it in the future. So the automatic curriculum generation can table a task if it's too hard right now and come back to it later. GPT-4 also hallucinates certain aspects of Minecraft that didn't exist, like a copper sword. Hallucinations also occur in the code generation process. GPT-4 sometimes hallucinates the control primitive APIs. On Wednesday, we had a presenter, Silan, present Gorilla. I think this might be an interesting application of Gorilla, where if you fine-tuned a model specifically on the control primitive APIs within Minecraft, you could probably eliminate a lot of the code generation errors that come from those API hallucinations. So some related work, Minecraft's an open 3D world game. There's been prior work within specifically reinforcement learning about trying to teach agents how to play Minecraft. There's also been work about teaching and training agents by having them watch a bunch of YouTube videos on how to play Minecraft. There's prior work called Dreamer V3, which has the agent learn a new world model to explore the environment. Some related work to this is high-level planning and the ability for LMs to create plans and decompose high-level tasks into several sub-goals and subtasks. There's been some recent work specifically on how to apply LMs and task decomposition to Minecraft and Minecraft recipes for crafting. So Voyager also uses an LM as a high-level planner, specifically GPT-4, and uses the Mind Flare, which is a level controller, following some prior works. The new addition to the field that Voyager provides over previous works is that Voyager employs an automatic curriculum generation, which enables more open-ended exploration than prior works. Inner monologue, which we talked about a few papers ago, incorporates environmental feedback. There's a lot of prior work on agent planning, things like chain of thought prompting, reflection, self-reflection, self-critique. AutoGPT combines a bunch of these. I think Dara was an interesting example they brought up, where Dara frames a task as a dialogue between two GPT-4 agents. I think that might be an interesting paper for us to read later on. And then generative papers, the generative agents paper, which was the simulacra paper, where all the little agents inside the sims planned a party together. That was another simulation of human behavior by storing agents' experiences, memories, and retrieving those for planning. Although the agents in that simulation didn't have executable actions within the world. So for code generation, Voyager's unique contribution to the field that's new is that it incorporates environmental feedback, execution errors, and self-verification. The self-verification is to assess task success, and it takes all of that context into an iterative prompting mechanism, which allows it to more accurately generate code. Yeah, Voyager is quite good at Minecraft is essentially the conclusion. What are some people's thoughts on the paper?
Promising.
Yeah, definitely.
And it also looks like they fully open sourced this Voyager on GitHub, which is even more cool because whatever questions are not clear from the paper can be looked up in the code.
Yeah, it's very nice.
Are all the skills that it used, like the skill index, is it all generated?
I believe so. I believe every skill in the skill library was created by Voyager itself. Because essentially to start out in Minecraft, you don't need any tools or skills. You start from nothing. So in order to have Voyager have the compounding knowledge that it gains by building all the skills iteratively, there's really no way to like shortcut that experience, I think.
Hey Sam, I have a question.
Yeah.
You know how have you played Minecraft?
A little bit many years ago.
Do you remember the setting in the achievements where it was basically a flowchart of the different things that you needed to do in the game to get to the end goal, which would be the Nether portal?
Yes. Yeah.
Did they use that at all?
No. So they didn't actually really play at all or have the agent even try and pursue, like, I guess what I would call Minecraft like story mode. Like, they essentially use Minecraft as an open-ended world that has no goal or no way to quote unquote win.
Okay. All right, just checking.
Yeah.
Yeah, I have a question.
Yeah.
In their skill library, did they? I didn't see any mention. Do they have the ability, once they commit something to the skill library, is it just stuck there the way that it was put there initially, or do they ever improve a skill?
There's like one sentence that sounds like Voyager might be able to improve skills that are already pre-existing in its library. They don't really talk about that at all. I think that might be something interesting to look in the code for.
I see.
Yeah.
Yeah. The other thing I didn't get a sense for is, so all their baselines, they seem to sort of saturate. They get stuck after, sort of learning, getting a certain number of different types of objects. Did they talk about Voyager? Like, does it also saturate, or did they not find like an upper bound?
It didn't seem like they found an upper bound, at least based on the graph. It doesn't seem. They spoke about how if they ablated certain components of the architecture, that it would plateau. But the complete Voyager architecture seems to be able to continuously improve. I guess, although there's a skill ceiling in Minecraft.
Yeah. So until they run out of money or something.
Yeah.
Cool.
Do they say how many skills they learn, and also like how many levels of skills there are? Like they might have like one basic skill, then later on have another skill that uses the one, and you'd have like a third level where it uses, level 2 skill, something like that.
I don't think they talk about skill levels. They talk a bit about the different levels of tools and crafting within Minecraft. But the answer to your question might be in the appendix. Let me see.
Also like the number of skills that they have.
Yeah.
Is it safe to?
Okay.
Yeah, sorry. I'm curious. Is it safe to assume that their long-term memory boils down to ever-growing library of skills with descriptions that are looked up using a vector database, or do they have any sophisticated memory on top of that?
It seems like it's just that.
So basically, they leverage the fact that the skills which are code. Yeah, that's actually that's very clever. Basically, they leverage code becomes their memory.
Douglas?
I'm looking at the code for that right now, so I just linked in the chat there the skill manager code for the Voyager paper here. And so they're using ChromaDB, and they're just doing a top K retrieval based off of OpenAI embeddings as their vector on their vector database. And so they're just doing the, I think, default top K retrieval from Chroma, which I think is just doing like your similarity matching off of that.
Yeah, they're using ADA, so they're probably using cosine as their distance metric because your distance
Yep.
metric is usually tuned to your embedding model. Yep.
Yep. And I see generate skill description here, but I don't think they have any way of modifying skills. So I think they can retrieve skills and they can add new skills, but I don't think there is a way for them to modify existing skills.
Yeah, like if you go to page 19, Sam, there's a pseudocode of the overall algorithm. Essentially, this way it seems it works, and I haven't verified it by looking at the base source code. The pseudocode seems to imply that the way it modifies a skill is by building on top of it, or just ignoring it, trying the loop again, and if it works, it'll just use that. And then that gets added back into the database. So when you do your embedding search the next time around, what looks like it'll happen is it might get a hit off both skills, the shittier older skill version of the skill and the newer better version of the skill. And I don't know if that might cause certain plateauing behavior later on down the line because they limit the results to 5 coming back from the database. But that seems to be how it's both improving its abilities as well as remembering things, back to the other previous question, because that's how it remembers stuff. So like, for example, if it's going to go get a bunch of wood somewhere, it actually stores the code to go get the wood. And in the code, it has the location of said wood.
Okay.
So
it writes
the
increasingly more specialized skills almost.
Exactly.
Okay.
Well, at least that's what the pseudocode seems to imply.
Yeah.
so the skills that they retrieve, and they retrieve the top 5 relevant skills and they put that back into the prompt, right? Did they put the entire code block into the prompt for all the retrieved skills?
I'm not sure what the formatting is for the prompt. I assume it's probably the natural language description of the skill, and then the little code snippet it would need to run to use it.
Yeah, it's on page 26.
Perfect.
Essentially, you can see it essentially pipes in a bunch of the previous code snippets and then says, okay, now figure it out.
Okay.
So do you mean that when it comes up with skills, those skills are tightly coupled with the actual environment the agent is in? So it may put hard code coordinates and stuff like this into skills, and these skills are only effective for the environment the agent is in.
Yeah, because it doesn't seem to have any other form of memory as far as like locations. And if it couldn't even remember the locations within the environment, then it wouldn't be able to move around. It would just keep on going in a circle.
Right, but it's still very clever because compared to that paper from Stanford about generative agents, they came up with a very sophisticated and elaborate memory system. But here, basically, simply code is leveraged.
Yeah.
Which makes the whole thing much simpler.
Yeah, I guess the goal is a bit different here. Like specifically within the simulacra paper from Stanford, they were trying to build agents that had long-term memories about personal interactions with other agents. So the kind of memory you need is inherently different. But for the problem they're working on in Voyager, their implementation is very smart.
All right, yeah, it makes sense. You're right. There, they explore social aspects, and here we just explore physical case. Those are two different problems.
Any other questions? If not, we have a guest presenter on Monday, and I'll see you all there.
Can I ask what the guest presenter is presenting?
Recurrent GPT, I think.
It's me, probably.
Yes, probably then.
Yeah, so I'll be the presenter. Thank you.
Yeah, perfect. Excited for it.
Good stuff,
Thank you,
guys.
Sam.
Enjoy your Friday.
Thank you, Sam.
Yeah.
Thanks.
Thanks for the presentation.
Bye.
Thanks a ton.
Thank you, Sam.